My name is Aman Puri, and here we will be calculating the mass of a black hole due to the mass of a star and the gravitational force in between the two and on each other. To calculate the mass of the black hole, we need to have some understanding of the motion of orbit, of how the star will orbit, and we need to have information about the forces, the perpendicular and parallel forces that are present in the system and surroundings. You can see the equations that we use in our computational model. F net is equal to the parallel plus perpendicular components of that. Here is what the parallel and perpendicular components are equal to. And then to finally calculate the mass, we will use Newton's law of universal gravitation and rearrange this formula to calculate for the mass of the black hole. Our gravitational constant is here. Our time is a day, which is 86,400 seconds. On the xy plane, the mass of the orbiting star is 2 times 10 to the 30. And using these numbers, we will calculate the unknown mass in our computational model. Calculations that we have to input in order to document the motion of the star orbiting the black hole. Here you see we have the momentum, the initial and final momentum is equal to m times v. And then you have delta v is equal final minus initial, same with momentum. And then you can set this equal to delta, which change of momentum over change over time, which is equal to the net force. And then you can find your parallel net force using these calculations. And then your perpendicular net force plus your parallel force is equal to F net, so F net minus the parallel component will be equal to the perpendicular. That the equation from earlier for the force of gravity is rearranged to solve for the mass. This is then input into GlowScript to print the mass for every iteration. In addition, the calculations earlier were used to document this motion here, and the average of all these calculations is equal to 1.049 times 10 to the 37th kilograms, which is the mass of the black hole, calculated by the average of all of the GlowScript calculations, as the calculations will be different for different positions in the motion. 2, using the values that we calculate in part 1, we can calculate the velocity to, actually this should say exit the orbit, which is 10 times 10 to the 7th power. This is calculated by setting the kinetic energy equal to the gravitational force, and this will yield this equation, which we can use to solve for the escape velocity. GlowScript code for part 2 of the lab, don't crash. So this is the position vector given by the planet, and then the velocity is updated to the escape velocity, and as you can see, when it is run, we escape the orbit of the black hole and get away from it. Differences between the change in momentum and the net force. So you can think about it like the net force is what causes the motion of the object. You can think about this in the parallel and perpendicular axes. And then the change in momentum is a reflection of the causal motion, which is related to the change in velocity and acceleration. However, these values are the same numerically. What does this mean to get into the orbital velocity? So you need a velocity high enough to counteract the centrifugal force and not fall towards the source of gravity. So you're going to set your normal component equal to mv squared over r. The normal component is obviously the gravity, which is the force that's acting on the things in orbit. And then you can solve for velocity by canceling out the mass and radius and getting this equation right here.